When ethane and oxygen are mixed in a closed container, the following equilibrium is established. Let's look at this equilibrium before we unpack it too much. We've got gas, 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 and gas. So let's look at the gas moles. 2 plus 7 is going to be 9 gas moles on the left, and 10 gas moles. 6 plus 4 is going to give me 10 gas moles on the right. Delta H is greater than naught. That means that this is an endothermic reaction. Notice that I'm writing this all down before I even consider the questions. And let's see what they now ask me. If I decrease the pressure, the system will favor the side with the most gas moles. So it will favor forward. If it favors the forward reaction, what will happen to the concentration of CO2? CO2 is in the product, so that will increase. The temperature is increased. An increase in temperature always favors the endothermic reaction. The forward reaction is an endothermic reaction, and therefore I am going to increase the concentration again of the CO2 because I favored the forward reaction. Delta H has got nothing to do with temperature. It's energy of reactants and energy of products, and that's your delta H value. So it's not going to change if I change the temperature at all. So this is going to be remains constant. If I add a catalyst, it does not affect the equilibrium position at all, and therefore this is also going to be remains constant. It reaches the equilibrium faster, but it does not change the equilibrium position, so it won't change the concentration of the CO2. The pressure is changed at a constant temperature by adding helium. If I push helium into the system, I am going to increase the pressure. Increasing the pressure is going to favor the side with the least gas moles, so it's going to favor reverse. By the way, putting in helium isn't part of this reaction. Helium is also a noble gas, which means it's highly unreactive and will do absolutely nothing in terms of changing the reaction. It will only change the pressure. So it's going to favor the reverse reaction, so the amount of CO2 will decrease. Give reasons for 1.3. As I said, delta H does not change. It is a difference between the energy and of the product and the reactants. It's not a function of temperature, so we've explained that over there. Explain your answer for 1.4. Catalysts do not change the equilibrium position. They simply make the equilibrium be reached faster. And 1.5 is that helium will not react with any of the species that are inside the container, and it will simply increase the pressure and favor the side with the least gas moles, which means that you will favor the reverse reaction and decrease the carbon dioxide. All of these can be answered in bullet points. I'm going to just do 1.5 as a bullet, so in bullets, because the shorter and sharper your answers are, the better. So, helium. So my bullet points are: the helium does not react. Pressure increases because there are more particles. It favors the side with the least gas molecules or gas moles. Reverse is therefore favored, and if you want to, you can write 9 is less than 10, and concentration of CO2 decreases. Consider the following reaction. We've got sulfur dioxide and oxygen forming sulfur trioxide, and my delta H value over here means that it is exo because it is a negative value, so it's an exothermic reaction. My gas moles are 3 gas moles on the left and 2 gas moles on the right. So, how does the rate of the forward reaction compare with the rate of the reverse during the following intervals? Between O and A, you can clearly see you're getting more SO3. So, the rate of the forward reaction is greater than the reverse. Between B and C, you can clearly see that I'm getting less and less SO3, which means I must be favoring the reverse reaction, so the forward reaction is less than. Between D and E, my SO3 is remaining stable, and therefore it is equal to, the rates are equal. If the changes in the graph from B to D are due to changes in temperature, so from B to D, at which point will the temperature be the lowest? Give an explanation of your answer. So it's quite a tricky question, but let's go through it anyway. If the reaction is an exothermic reaction, low temperature favors the exothermic, but you can see between B and C that I'm actually favoring the endothermic. So I'm increasing the temperature between B and C, and therefore it would be hottest over here before I start favoring the exothermic reaction again. So the hotter I make it, the less SO3 I'm going to have. So that will be the hottest point. So if the changes are due to temperature, at what point will the temperature be the lowest? Well, this is going to be the hottest point. So this will be the coldest point. So it will be B. Why? Because cold favors exo, therefore most SO3, and exo, by the way, is forward. Most SO3 is coldest point. If the changes in the graph are due to pressure, at which point will the pressure be the lowest? Given explanation. So pressure, we want 2 gas moles versus 3 gas moles. High pressure will favor lots of SO3. So that's high pressure. This is low pressure. And let's explain that. So the lowest pressure will be at point C. Low pressure favors most gas moles. And in that case, this case, that is the reverse. So when is the reverse most favored? When I have the least SO3. Least SO3 is lowest pressure. Hope that makes some sense. Here we've got a diagram of an energy profile, and you may wonder why we're doing an energy profile. We're not doing rates, because rates and equilibrium are really, really intertwined with each other. So what is meant by the term activation energy? This is the definition, and it means the energy required to start a reaction or to reach the activated complex. You just need to get these definitions down. Calculate the change in energy for the forward reaction. So the reactants between here and here is 40, between here and here is 20. Therefore, this space here must be 20. So delta H is 20 kilojoules per mole. How would you classify the forward reaction? The reactants have got less energy than the products, so it must be an endothermic reaction. Following diagram shows concentration. So you're looking at concentration. It's not the rate of products and reactants initially at equilibrium. So they start off all with constant concentrations against time. The reaction is HI becomes H2 plus I2. Is the system at equilibrium at 10 seconds? No, because clearly the concentration of everything is changing at that point. So no, all concentrations are changing. And concentrations stay the same when you are at equilibrium. Which external factor was applied to the system to bring about the change at 5 seconds? So obviously something happened over there. I've got 2 gas moles on the left and 2 gas moles on the right. So it obviously wasn't pressure, because a change in pressure is not going to change the equilibrium of this particular system. As well as the fact that if I change pressure, I'm going to, if I squash the system, all the concentrations will increase. If I release pressure on the system, all the concentrations would decrease. So it's not going to be pressure. This is a delta H is greater than, this is an endothermic reaction. So if I now favored, up goes the products. So I have favored forward. Therefore, I have favored endo. Therefore, I must have increased temperature. Explain how that factor caused the change. I've just done that explanation. So they tell us that this is an exothermic reaction. So sorry, this is negative 49. It's not 49. So it's an exothermic reaction. And an exothermic reaction, we need to know what's going to happen if I increase the pressure on HI and H2I2. In fact, they're only interested in HI, but I've got 2 gas moles on the left and 2 gas moles on the right. So the pressure amount, by the way, means number of moles. And it's going to make no difference to the number of moles. It might make a difference to the concentration because obviously I'm going to squash everything together, but I'm not going to change the number of moles of HI. So there will be no change to the number of moles of HI. The effect of removing some I2, if I take I2 out, the system will favor the reverse reaction. The reverse reaction is going to mean that there will be less HI. Let's see what they ask. Removing I2 at equilibrium from the reaction mixture on the amount of H2. Well, it means I'm going to make more H2 because the system's going to try and compensate. So more H2 will be formed. Why? Because I2 removed, therefore system tries to make more I2, therefore reverse favored, and that in turn favored, and that in turn means that you're going to land up with more H2. If they had asked me about temperature, what if I had increased the temperature? If I increased the temperature, I would have favored the endothermic reaction.